Chapter 1, the problem begins. Let's start with something simple. Two objects in space. They pull on each other through gravity. One object orbits the other in a smooth, predictable path. We've known how this works for centuries. The Earth orbits the Sun. It does so because of gravity, a force described by Isaac Newton. This kind of motion, involving just two bodies, is called a two-body system. We can describe it exactly. We can write down equations. We can predict what will happen, years, even centuries into the future. Now, let's add a third body. Introduce the Moon. Now we have three objects, the Earth, the Moon, and the Sun. Each of them pulls on the others, constantly. The Moon pulls on the Earth pulls on the Moon. The Sun pulls on both and is pulled in return. This is where things get complicated. This is called the three-body problem. The question seems simple. If we know the starting positions and speeds of three objects, can we calculate where they'll be in the future? In theory, yes. In practice, not so easily. The problem lies in how gravity works. Each object affects the other two. Every movement changes the forces, and every change in force changes the movement. It loops back over and over. Even a small change at the start, barely noticeable, can lead to massive differences later. This is what scientists call chaotic behavior. But here's something important. Not all three-body systems fall apart. The Earth-Moon-Sun system, for example, is relatively stable. It wobbles, it shifts slightly, but overall it holds together. That balance is delicate. It works because of the specific masses, distances, and speeds of the bodies involved. This balance allows us to predict eclipses, tides, and orbits with great accuracy. But elsewhere in the universe, the picture is very different. In systems with 3 stars or planets near 2 suns, chaos is common. Some objects get flung out into deep space. Others spiral into collisions. Some enter loops that change shape constantly with no clear pattern. In these cases, long-term prediction becomes nearly impossible. So why does this matter? Because the three-body problem touches everything in space. It helps explain how star systems form or fall apart. It affects how we plan spacecraft missions. It connects to chaos theory, a major idea in modern science. And it reminds us of something deeper. Even in a universe governed by simple laws, outcomes can be unpredictable. Chapter 2. The struggle to solve it. The three-body problem is not new. In fact, it has been known and feared for hundreds of years. The issue wasn't that scientists didn't understand gravity. They did. It was that gravity, when shared between 3 bodies, created a system too complex to tame. The story begins in the late 1600s. Isaac Newton had just published his Philosophiae Naturalis Principia Mathematica, a work that explained how gravity worked between 2 objects. His equations were precise, elegant. They worked. Using Newton's laws, one could predict how planets move, how apples fall, and how moons orbit their planets. 2 objects, no problem. But as Newton himself discovered, the moment a third object entered the equation, certainty began to dissolve. Even Newton struggled. He was interested in the moon. More specifically, how the moon was affected not just by Earth's gravity, but also by the sun's. He tried to calculate the moon's motion using his laws, but the numbers didn't quite match reality. The moon wobbled in ways he couldn't explain. He called the problem embarrassing. Newton wasn't alone. Many scientists after him, brilliant mathematicians, tried to solve the three-body problem. They believed it was just a matter of finding the right equation, a hidden formula, an elegant shortcut, something that would unlock the full motion of 3 objects, the way Newton had unlocked 2. But the problem was deeper than that. Each time someone tried, the math grew more complicated. The equations got longer, the solutions more unstable, and small errors in the input caused huge errors in the output. Still, they didn't give up. In the 1700s, the great mathematician Leonhard Euler proposed solutions, clever approximations that worked in some cases. Then came Joseph Louis Lagrange, who discovered something remarkable. Under certain conditions, 3 bodies could maintain a stable arrangement. He found specific points in space, now called Lagrange points, where a smaller object could remain fixed relative to 2 larger ones. These points are not just theoretical. Today, we place satellites there. We use Lagrange points to keep telescopes and probes stable as they observe space. But these discoveries didn't fully solve the problem. They only provided solutions in narrow, idealized cases, like when one object is much smaller than the other two, or when the bodies are perfectly aligned. Real systems, with real motion, real imbalances, and real irregularities, remained unpredictable. Then came the 1800s. In 1887, a Swedish king offered a prize: solve the three-body problem completely with a general solution and win the gold. Many tried, but it was Henri Poincaré, a French mathematician, who made the breakthrough, except it wasn't the breakthrough they expected. Poincaré didn't solve the problem. He proved it was unsolvable, at least in the way people hoped. He showed that the motion of three gravitational bodies could be so sensitive to initial conditions that long-term prediction was impossible. This was a turning point. It was the birth of something new: chaos theory. Poincaré's insight was subtle but revolutionary. He realized that even in a system governed by precise laws, the outcome could still be unpredictable. Not because the laws were wrong, but because the system itself amplified tiny differences too small to measure. This discovery changed physics. It changed mathematics. It forced scientists to stop searching for a neat solution and instead begin studying the behavior of systems that could not be solved exactly. The three-body problem became a doorway, not just to celestial mechanics, but to a new understanding of complexity. Chapter 3: When Machines Took Over. By the early 20th century, the limits of human calculation were clear. Mathematicians had spent centuries trying to predict the motion of three interacting celestial bodies using pen, paper, and theory. Despite scattered successes in special cases, no general solution emerged. Then, something revolutionary happened, not in the sky, but on Earth. We built machines that could think in numbers. At first, they were slow, mechanical, bulky, but what they lacked in elegance, they made up for in persistence. A human might tire after a few dozen calculations. A computer could perform thousands every second without pause. This changed everything. Now, instead of seeking a single formula to solve the three-body problem, scientists could simulate it. They could input the starting positions of three bodies, their velocities, their masses, and let the machine calculate what would happen next. Not all at once, but step by step. This approach is called numerical integration. It doesn't give you a neat equation. Instead, it gives you motion, broken into time slices. First, the computer calculates what happens in the next second, then the second after that, and so on. Each step uses the results of the last. The process continues forward through time, painting a picture of how the system evolves. This method isn't perfect. Small errors can still grow, just like Poincaré predicted. But with careful programming and precise input, it reveals what had previously been hidden: the actual behavior of complex systems. And what it revealed was extraordinary. In some simulations, the three bodies danced in ways no one had ever imagined. They looped and spiraled, passed close to one another, then flung apart, only to reunite later. Sometimes two bodies would form a tight pair, with the third orbiting far outside, only to swing in and disrupt the balance. Other times, one body would be ejected entirely, tossed into deep space by the gravitational tension between the remaining two. These were not theoretical possibilities. They were real outcomes, rendered on screen. They didn't follow the old patterns of neat circles and ellipses. They were chaotic, sensitive, and endlessly varied. One of the most surprising findings came in the form of stable chaos. Certain starting configurations, when run through a computer, produced what looked like unpredictable motion, but the system never fell apart. The paths were tangled, but they didn't unravel. It was like watching a complicated dance, wild, unscripted, yet held together by invisible rules. In some cases, repeated simulations showed signs of order within chaos. This led scientists to begin asking new questions. Not, can we solve the three-body problem? But, what kinds of behaviors are possible within it? How many patterns exist? Are there families of motion that repeat? With better computers came deeper exploration. In the late 20th century, researchers discovered strange and beautiful solutions hidden within the chaos. Some orbits repeated themselves. Others formed symmetrical paths, with all three bodies moving in perfect coordination. One famous example is the figure-8 orbit, discovered in 1993. In this configuration, all three bodies chase one another along the same path, an endless looping figure-8 without colliding or escaping. It was unexpected, it was precise, and it was stable. This was not what chaos was supposed to look like, but it was real. Thanks to machines, scientists could now test millions of starting conditions. They could build maps of behavior, catalog chaotic paths, isolate stable ones, and slowly a new kind of understanding emerged. Not an equation, but a landscape. A behavioral map of the three-body problem, built through simulation, not symbols. The machine didn't solve the problem, it didn't break the laws of chaos, but it gave us a way to explore it, to watch it unfold, to replay it, to learn from it. It turned the three-body problem from a riddle into a world, one that could be studied, visualized, and even navigated. Chapter 4: Patterns in the Storm. By now, we understand something crucial. The three-body problem is not just hard, it's unpredictable in a very specific way. Small changes at the start can lead to wildly different outcomes. That's chaos. But chaos doesn't mean random, not quite. And this distinction changed everything. In the age of computers, scientists started to notice something unexpected in their simulations. Even among the swirling, looping, chaotic motions of three celestial bodies, certain patterns kept appearing. They weren't obvious, they weren't simple, but they were there. This led to a question that changed how physicists viewed the entire problem. Could chaos have structure? Let's start with something familiar: symmetry. In physics, symmetry is often a sign of stability. If something looks the same when you rotate it, reflect it, or shift it through time, it usually obeys some deeper rule. And within the chaotic sea of three-body motion, symmetric configurations began to emerge. One of the most stunning is the figure-8 orbit. Three identical masses follow the same looping path, like runners chasing each other in a constant, synchronized figure-8. They never crash. They never drift apart. The entire pattern repeats again and again. This solution wasn't discovered with pencil and paper. It was found by letting a computer test thousands of starting conditions until something clicked. The result was not only beautiful, it was precise. And it wasn't alone. In the years that followed, more of these stable orbits were uncovered. Some formed tight triangles that rotated and flipped. Others looked like celestial knots, weaving in and out of themselves but never unraveling. Each orbit was a kind of dynamical sculpture, shaped by gravity, carved by motion, preserved by symmetry. They weren't obvious, they weren't intuitive, but they were stable. Why do these patterns matter? Because they suggest that the three-body problem isn't just a mess of unpredictable motion, it's a spectrum. On one end, complete chaos, bodies flinging apart, never to return. On the other, fragile harmony, orbits that loop forever without breaking down. And in between, a vast middle ground of semi-stable systems where motion seems chaotic but obeys hidden rhythms. Physicists began to map this space. They built what are called stability charts, diagrams showing which combinations of mass, position, and velocity led to stable motion. Think of it like a weather map for gravity. In some regions, conditions are calm. In others, storms rage. And somewhere in between, small islands of order float in an ocean of chaos. This work revealed a powerful idea. Stability isn't just rare, it's structured. It forms pockets, it clusters, it repeats. But only under the right conditions. Change something, just a little, and the system might slide from order into chaos, or back again. This insight reshaped not just our understanding of gravity, but the way we approach prediction itself. In simple systems, you ask, what will happen next? In complex systems, you ask, what kinds of things can happen? It's a shift from precise forecasting to pattern recognition, from individual outcomes to classes of behavior. The three-body problem became a kind of gravitational language. One where each orbit, each twist and loop was a sentence written in motion. And scientists, with their simulations, maps, and mathematical tools, became readers of that language. These patterns, once hidden, now guide everything from space exploration to planetary science. They help us understand where moons can safely orbit, where spacecraft can fly without being pulled off course, and even how distant stars might organize their planetary systems. The storm, it turned out, had structure, and the chaos had a shape. Chapter 5. The universe is a three-body lab. We've talked about simulations, we've seen mathematical patterns, but the three-body problem isn't confined to chalkboards or computers. It's out there, in space, happening right now, all across the universe. If you look up at the night sky, you might see a single star, but that's not the full picture. Many stars, perhaps even most, aren't alone. They come in pairs or triplets. These systems orbit each other, held together by gravity. They are natural laboratories of the three-body problem. Let's start with triple star systems. Three stars, bound by gravity, moving around a common center. Astronomers have catalogued many of these. Some are widely spaced. One star orbits two others from a distance. Others are tight and compact, all three stars orbiting in close gravitational interplay. These systems are difficult to understand without the tools we've discussed. They can be stable for millions of years, or unstable, flinging one star out like a slingshot after a brief cosmic dance. Even stranger things happen when planets enter the picture. Imagine a planet trying to orbit a pair of stars. This isn't science fiction, it's been observed. These are called circumbinary planets. Like Tatooine from Star Wars, they orbit two suns instead of one. Their motion is complex. The gravitational pull from each star changes constantly, reshaping the planet's path moment by moment. For a long time, it was unclear if such planets could even exist. The gravitational environment seemed too chaotic, but now we know they can and do, but only if they form at just the right distance, outside the zone where chaos would tear their orbit apart. The three-body problem explains why. It tells us that only certain orbital paths are stable. Others decay over time. Planets drift, or collide, or are hurled into deep space. So if a planet survives, it's because it lives in one of those rare zones of stability, a safe lane in a chaotic gravitational highway. This insight is useful. It tells scientists where to look. If you know the layout of a star system, and you understand the rules of three-body dynamics, you can predict which orbits are likely to be stable. That narrows the search for exoplanets. It guides telescope time. It helps us interpret the wobbles and shadows in starlight that hint at orbiting worlds. But the influence of the three-body problem doesn't end with stars and planets. It reaches into the very structure of galaxies. In dense clusters of stars, gravitational interactions are constant. Stars pass close to one another, and brief three-body encounters are common. These interactions can rearrange the system. One star might capture another into orbit, only to have the third disrupt the pair. These encounters change star speeds, alter trajectories, and even eject stars from their galaxies entirely. There's a name for these: hypervelocity stars. They're real. They move faster than almost anything else in the galaxy. Many are believed to have been launched by three-body interactions near the center of the Milky Way, close to the supermassive black hole. Even black holes themselves can form triple systems. When galaxies merge, their central black holes may orbit each other, sometimes forming tight trios. Simulating such systems is a direct application of the three-body problem, but now with space-time itself being warped, as relativity enters the picture. We'll return to that later. What matters now is this: the three-body problem isn't rare. It's everywhere. It shapes where stars live, how planets survive, which systems endure, and which collapse. We've moved from equations to simulations, from simulations to patterns, and now from patterns to the real cosmos. Every step has taken us deeper, from abstract math to the mechanics of nature itself. But we're not done yet. There's one more direction to go. We've looked outward. Next, we'll look forward, toward technology, exploration, and the future of spaceflight. Because as we begin to send spacecraft into more complex gravitational zones, near moons, planets, and stars, the three-body problem becomes more than a concept. It becomes a navigation challenge, a test, and perhaps an opportunity. Chapter 6: Gravity's Game of Dice. For centuries, the three-body problem was a curiosity, a puzzle, a phenomenon observed in distant stars and simulated on Earth. But now it's something else. It's a real-world problem for mission planners, space agencies, and spacecraft designers. Because the moment we leave Earth, we enter a gravitational web, one shaped by more than just one or two objects. And if we want to move through that web efficiently or safely, we must understand the strange dynamics that govern it. When a spacecraft leaves Earth, it doesn't travel in a straight line. It falls through space, guided by the gravitational pulls of Earth, the Moon, the Sun, and even other planets. Each pull bends its path, each mass warps the trajectory, and depending on timing and distance, those forces can work together or against one another. Navigating this environment means managing a multi-body problem. In some missions, it's close to a two-body case, like a probe falling toward the Moon under Earth's gravity. But most of the time, there's a third influence. Maybe it's the Sun, maybe a planetary moon, maybe another planet altogether. And that's when things get complicated. Traditional methods of trajectory planning assume predictability. They assume we can calculate a path, then follow it. But in a multi-body system, even tiny errors in course, a fraction of a degree, a second's difference in launch time, can lead to entirely different outcomes weeks later. A ship might pass cleanly between two bodies, or crash into one, or slingshot into an unexpected orbit. It's a gravitational game of dice, one that doesn't forgive imprecision. So how do we deal with it? We adapt. We lean into the chaos and learn to navigate through it. One approach is to use chaotic regions in space as highways. It may sound counterintuitive, but the same gravitational complexity that makes prediction difficult can be used to reduce energy costs. By carefully entering a region where multiple gravitational pulls intersect, a region where motion is naturally unstable, a spacecraft can be nudged onto a new path with very little fuel. These paths are called interplanetary superhighways. They are invisible corridors, shaped by the gravitational fields of celestial bodies. They shift and weave through space, dynamic and ever-changing, but real. One famous example is the Interplanetary Transport Network. It's not a physical structure, it's a web of pathways discovered through the study of three-body dynamics that allows objects to travel between planets and moons using minimal propulsion. The catch? These paths are slow, sometimes indirect, and they require precise timing. But in long-term planning, for satellites, telescopes, and deep space probes, they offer extraordinary efficiency. In short, we use gravity to do the work. But to do that, we must understand the chaos well enough to ride it. This method was used in missions like Genesis and Grail, where engineers placed spacecraft in orbits that exploited unstable points between Earth, the Moon, and the Sun. Rather than fight the chaos, they let it guide the craft. Like a surfer waiting for the right wave, the goal is not to control the sea, but to read it. This strategy also relies heavily on Lagrange points, those rare places where the gravitational pulls of two large bodies balance perfectly, allowing a smaller body to remain in a fixed position. We touched on them earlier. But now they're more than just curiosities. They're strategic locations. Spacecraft can park there, with minimal fuel required to stay in place. The James Webb Space Telescope, for instance, orbits around L2, the second Lagrange point beyond Earth, a gravitationally quiet place from which it can observe deep space with minimal interference. None of this is possible without a deep understanding of three-body motion. And not just understanding, simulation. Every maneuver, every orbital insertion, every slingshot trajectory, it must be modeled in advance. We can't test these things physically. There's no practice run in deep space. So before any spacecraft launches, its path is simulated thousands, sometimes millions of times, under slightly different starting conditions. Why? Because of the three-body problem. Because tiny differences can grow. and we need to know all the ways the mission could go right and all the ways it could go wrong. This is the age we now live in, an age where navigation is non-linear, where success depends not just on force and fuel, but on timing, geometry, and sensitivity. In this new frontier, the three-body problem is no longer just a warning. It's a tool, a challenge, yes, but also a map. One that, if understood correctly, can reveal new pathways to the stars. Chapter 6: Gravity's Game of Dice. For centuries, the three-body problem was a curiosity, a puzzle, a phenomenon observed in distant stars and simulated on Earth. But now it's something else. It's a real-world problem for mission planners, space agencies, and spacecraft designers. Because the moment we leave Earth, we enter a gravitational web, one shaped by more than just one or two objects. And if we want to move through that web efficiently or safely, we must understand the strange dynamics that govern it. When a spacecraft leaves Earth, it doesn't travel in a straight line. It falls through space, guided by the gravitational pulls of Earth, the Moon, the Sun, and even other planets. Each pull bends its path, each mass warps the trajectory, and depending on timing and distance, those forces can work together or against one another. Navigating this environment means managing a multi-body problem. In some missions, it's close to a two-body case, like a probe falling toward the Moon under Earth's gravity. But most of the time, there's a third influence. Maybe it's the Sun, maybe a planetary moon, maybe another planet altogether. And that's when things get complicated. Traditional methods of trajectory planning assume predictability. They assume we can calculate a path, then follow it. But in a multi-body system, even tiny errors in course, a fraction of a degree, a second's difference in launch time, can lead to entirely different outcomes weeks later. A ship might pass cleanly between two bodies, or crash into one, or slingshot into an unexpected orbit. It's a gravitational game of dice, one that doesn't forgive imprecision. So how do we deal with it? We adapt. We lean into the chaos and learn to navigate through it. One approach is to use chaotic regions in space as highways. It may sound counterintuitive, but the same gravitational complexity that makes prediction difficult can be used to reduce energy costs. By carefully entering a region where multiple gravitational pulls intersect, a region where motion is naturally unstable, a spacecraft can be nudged onto a new path with very little fuel. These paths are called interplanetary superhighways. They are invisible corridors, shaped by the gravitational fields of celestial bodies. They shift and weave through space, dynamic and ever-changing, but real. One famous example is the Interplanetary Transport Network. It's not a physical structure, it's a web of pathways discovered through the study of three-body dynamics that allows objects to travel between planets and moons using minimal propulsion. The catch? These paths are slow, sometimes indirect, and they require precise timing. But in long-term planning, for satellites, telescopes, and deep space probes, they offer extraordinary efficiency. In short, we use gravity to do the work. But to do that, we must understand the chaos well enough to ride it. This method was used in missions like Genesis, and Grail, where engineers placed spacecraft in orbits that exploited unstable points between Earth, the Moon, and the Sun. Rather than fight the chaos, they let it guide the craft. Like a surfer waiting for the right wave, the goal is not to control the sea, but to read it. This strategy also relies heavily on Lagrange points, those rare places where the gravitational pulls of two large bodies balance perfectly, allowing a smaller body to remain in a fixed position. We touched on them earlier. But now they're more than just curiosities. They're strategic locations. Spacecraft can park there, with minimal fuel required to stay in place. The James Webb Space Telescope, for instance, orbits around L2, the second Lagrange point beyond Earth, a gravitationally quiet place from which it can observe deep space with minimal interference. None of this is possible without a deep understanding of three-body motion. And not just understanding, simulation. Every maneuver, every orbital insertion, every slingshot trajectory, it must be modeled in advance. We can't test these things physically. There's no practice run in deep space. So before any spacecraft launches, its path is simulated thousands, sometimes millions of times, under slightly different starting conditions. Why? Because of the three-body problem. Because tiny differences can grow, and we need to know all the ways the mission could go right, and all the ways it could go wrong. This is the age we now live in, an age where navigation is non-linear, where success depends not just on force and fuel, but on timing, geometry, and sensitivity. In this new frontier, the three-body problem is no longer just a warning. It's a tool. A challenge, yes, but also a map. One that, if understood correctly, can reveal new pathways to the stars. Chapter 8, The Code of the Cosmos. By now, we've seen it all. Gravitational tug-of-wars between stars, planetary systems with delicate orbits, space missions surfing invisible gravitational currents, and computers discovering strange new dances in the darkness of space. But beneath all of this, beneath the stars and algorithms and simulations, lies a deeper question. Can we ever really know what will happen next? That question doesn't come from doubt. It comes from the heart of the three-body problem. Because when three bodies interact under gravity, something peculiar happens. Not immediately, not obviously, but eventually, if you track the motion long enough, you notice something unnerving. Tiny changes in the starting conditions lead to huge differences in the final outcomes. A difference of a millimeter, a pause of 1 second, a shift in mass of 1 grain of sand. Any of these can change the whole story. This is known as sensitivity to initial conditions. And it's not just an interesting property, it's the very core of chaos theory, a branch of mathematics that grew directly out of the three-body problem. Let's be clear, chaos doesn't mean disorder, it doesn't mean randomness, it means this. The system follows strict laws, but it is so sensitive that we cannot predict its future for very long. That's the subtle terror of it. The universe is not rolling dice, it's obeying rules. But those rules amplify the tiniest uncertainties until they overwhelm our ability to forecast what happens next. This idea isn't limited to celestial mechanics. Weather systems do the same. So do ecosystems. So do economic markets and even neural patterns in the brain. But it was the three-body problem and the motions of planets that first revealed this hidden property of nature. It forces us to rethink what we mean by predictable. In a two-body system, prediction is perfect. The orbit is clean, repeatable, forever knowable. But the moment a third body enters the scene, the certainty begins to unravel. We can simulate, we can model. But beyond a certain point, all predictions dissolve into probabilities. Not because we lack computing power, not because we're lazy, but because the universe itself does not permit us to look too far ahead in systems like these. This insight has massive implications in physics, in cosmology, even in philosophy, because it suggests there are limits to determinism. If systems governed by simple laws can still behave unpredictably due to sensitivity, then perhaps uncertainty is a built-in feature of the cosmos. Here's a famous metaphor from chaos theory. A butterfly flaps its wings in Brazil, and a storm forms over the Atlantic. It's poetic, but it's also rooted in the same dynamics that make the three-body problem so volatile. In both cases, the early conditions shape the future, but the shaping is non-linear. It doesn't scale predictably. One tiny detail can eventually dominate the outcome. So what does this mean for science? It doesn't mean we stop predicting, but it changes how we predict. We stop asking, where will this object be in 100 years? And we start asking, what range of behaviors are likely? We think in terms of stability zones instead of fixed paths. We think in probability clouds instead of sharp trajectories. And in doing so, we shift from certainty to understanding, from control to insight. This is the real lesson of the three-body problem. Not that the universe is chaotic, but that it is structured chaos. It is not random, but it is fragile. It is governed by rules, but it is rich with surprises. And even when we know the laws, the Newtons, the Keplers, the equations of motion, we are still humbled by the depth of complexity they produce. Chapter 9. Interstellar architects. For a long time, chaos was a warning. It meant danger, instability, systems that could not be trusted. But over the last few decades, something changed. Instead of avoiding chaos, scientists began to harness it. They started asking, what if we could build systems that thrive in unstable environments? What if we could design for chaos, not against it? And from that question, a new class of thinkers emerged: interstellar architects. These are the scientists, engineers, and visionaries who are designing spacecraft, satellites, and even theoretical megastructures to coexist with, and sometimes exploit, gravitational unpredictability. To understand their challenge, imagine placing a spacecraft near three massive celestial bodies, say, Earth, the Moon, and the Sun. The gravitational pull is constantly changing. The craft is being tugged in multiple directions at once. Any traditional attempt to hold position would be costly, requiring constant thrust and fuel corrections. But what if, instead of resisting those forces, the spacecraft could ride them? This is where the concept of chaotic orbits enters the picture. These are trajectories that appear unstable, yet are predictable for long periods when managed carefully. Engineers have found that by timing the launch and maneuver phases precisely, a spacecraft can be placed on a path where gravity does most of the work, even in highly unstable regions. One real-world example is NASA's Artemis mission, which repurposed two Earth-orbiting satellites and sent them into lunar orbit using chaotic trajectories. The mission saved fuel and extended the satellites' lives, all by understanding and embracing the chaotic behavior of the Earth-Moon system. This new philosophy extends even further. In designing deep space probes, engineers are now experimenting with low-energy transfers between planets that use gravity and instability creatively. Instead of plotting straight lines or simple ovals, these probes travel along naturally unstable corridors, gravitational highways discovered through computer simulations. The result? Missions that use a fraction of the fuel, but require extraordinary planning and long-term precision. These paths are not intuitive. They are rarely symmetrical, and they often look like scribbles in space. But they work, because they follow the hidden logic of the three-body problem. Even more futuristic is the idea of self-stabilizing spacecraft. These aren't stabilized by brute force, with engines constantly firing. They are stabilized by structure, by being designed to respond naturally to gravitational shifts. Imagine a spacecraft with dynamic wings that shift position depending on its gravitational environment, like a bird catching a thermal current. Or a space station built near a Lagrange point that shifts mass internally to balance itself automatically. These systems would not fight chaos, they would synchronize with it. And that concept is being explored not just for satellites, but for the future of human settlements beyond Earth. Nowhere is this idea more radical than in the realm of megastructures. These are theoretical constructs far beyond our current capability, but possible within the laws of physics. One example is the Einstein-Rosen ring, a hypothetical structure that could orbit in a three-body system in such a way that its motion is sustained by the changing gravitational fields. Or the concept of a gravity-anchored array, a massive telescope or sensor platform that drifts inside the gravitational triangle formed by three orbiting bodies. These structures would require continuous micro-adjustments, and they would rely on detailed knowledge of three-body dynamics to survive. But in theory, they could exist. In fact, their existence may be easier in chaotic systems, where stability is not fixed, but dynamic. This shift in mindset is crucial. It means moving away from static engineering, where everything is locked in place, and toward adaptive engineering. It's the same shift that happened in biology. Organisms don't resist change, they evolve with it. Now space technology is beginning to do the same. One of the driving forces behind this revolution is the increased power of simulation. Using modern computational tools, engineers can model the gravitational behavior of a spacecraft over decades under trillions of conditions. They can search for those islands of temporary stability in a sea of chaos. And once found, those islands can become homes for human technology. So far, we've used this knowledge mostly for satellites and probes. But what happens when we apply the same thinking to planetary defense or interstellar travel? Can chaos help us slingshot to the stars? Can it hide objects or protect them inside gravitational shadows? These questions are no longer theoretical. They are becoming part of the planning discussions at space agencies, defense organizations, and research institutes around the world. Because in the three-body problem, unpredictability is inevitable. But with the right tools, it's also navigable. We are learning to design not for perfect stability, but for controlled complexity. We are becoming architects of motion, shaping our technologies to match the dynamic nature of the universe itself. Final chapter, the edge of reason. There are few problems in science that stretch across so many domains, and yet remain so elegantly contained as the three-body problem. It begins with the simplest of premises, three objects, each pulling on the others by gravity. And yet from that simplicity, it opens into a vast, ever-changing wilderness, mathematical, physical, even philosophical. We chased it through ancient skies and handwritten star maps. We met it again in the notebooks of Newton and Euler. It trickled through the chalkboards of great minds, resisted exact solutions, and gave birth to chaos theory. Then, silently, it helped guide spacecraft across millions of miles. We followed it to triple star systems. We let machines map its hidden patterns. We saw engineers bend its chaos into useful tools. And somewhere along the way, we began to accept a deeper truth, that not everything in the universe is meant to be solved. Some things are meant to be explored. The three-body problem doesn't exist in isolation. It's not just about three objects, it's about interaction, about the delicate consequences of relationship. Each motion affects the others. Every force ripples through the system. This mirrors so much of what we see in nature, in ecosystems, in societies, even in personal lives, where individual actions intertwine and outcomes emerge not from a single cause, but from the complex dance of all participants. It reminds us that the world is not made of isolated parts. It is made of connected systems, and that those systems can be unpredictable, yet still governed by deeper laws. There's a beauty in that unpredictability, not because we cannot control it, but because it reveals the richness of possibility. Every time we model a new three-body system, we see something different. Every new initial condition is a story waiting to be told, a choreography that has never been danced before. We could spend 1,000 years exploring these motions and still find new patterns. Not because the rules changed, but because the rules allow for endless nuance. This is what makes the three-body problem timeless. It is not a riddle with a single answer. It is a window into the kind of universe we live in. Perhaps that's why it has captivated thinkers for centuries. It invites humility. It reminds us that certainty has limits. It asks us to look deeper, think broader, and accept that even in pure mathematics, there are horizons beyond calculation. And at the same time, it leaves us with awe that from something as ordinary as three falling bodies, we can glimpse the full complexity of space, time, and structure. So we leave the problem not with a final solution, but with a final understanding that complexity is not the enemy of reason. It is its most honest companion. That motion does not require a map, only a path. And that in the ever-shifting dance of the universe, it's not just the destination that matters. It's how we learn to move within it.